So, what makes the local potential to trigger an action potential? In the local potential, we saw that the sodium enters the dendrites and soma via ligand gated sodium channels. When they enter, the sodium diffuses across the nerve cell body until it reaches the axon hillock. When it does this, the voltage of the nerve cell body also changes and the voltage spreads across the entire nerve cell body. These arrows represent the wave of depolarization that spreads across the nerve cell body and it arrives at the axon hillock. The voltage has changed. It's no longer minus 70, it's probably 0 or minus 55 or minus 40, depending upon the strength of the stimulus. The minimum voltage needed to start an action potential is minus 55 millivolts. That's the minimum voltage that's needed. It can be higher, but it cannot be lower. We call this minimum voltage the threshold voltage. A threshold means an entrance or a doorway. In order to pass through the doorway and start the action potential, you need to have minus 55 millivolts because when this voltage is reached, another set of channels called voltage gated sodium channels sense the change in voltage and automatically open. And the sodium that's outside rushes in, and that starts the action potential. So the action potential is triggered by the opening of voltage gated sodium channels. You want to imagine voltage gated sodium channels to be like motion sensors, those sliding doors that we see. When they sense motion or movement, they automatically open. And the location for triggering an action potential is the axon hillock. Let's take a look at the events that lead up to the formation of an action potential. We started with the local potential and the wave of depolarization that spreads across the nerve cell body. This depolarization arrives at the axon hillock. Remember, the axon hillock is the site for triggering the action potential. Now we need to check the voltage. Is the voltage high enough? If the voltage is at least minus 55 millivolts, which we call the threshold voltage, then the action potential will be triggered. This is because anything above minus 55 millivolts will be sensed by voltage gated sodium channels, which will open. When these channels open, sodium that has been accumulating outside the axon will rush in. When sodium rushes in, it brings along with it positive charges. And this causes the membrane voltage to go up. When a membrane voltage increases and approaches 0, we say that the membrane is depolarized. So the next step is that the membrane depolarizes. This depolarization is fairly rapid because many sodium channels open at once, lots of sodium comes in, and this causes the depolarization phase of the action potential. So the depolarization phase of the action potential is triggered by the opening of voltage gated sodium channels. The range of voltage for the depolarization phase is from minus 55 millivolts to plus 20 millivolts. Let's do a quick review of the distribution of ions and the protein pumps and channels that are involved in the depolarization phase of the action potential. Remember, there's always more sodium outside the cell and there's always more potassium inside the cell. The sodium-potassium pump that is shown in red is always functional. The potassium leak channel that is shown in blue is also functional, allowing very small quantities of potassium to leave the cell. What we have here in yellow is the voltage-gated sodium channel, which triggers the depolarization phase of the action potential. During this phase, these channels are open and sodium rushes in, bringing positive charges into the cell and causing the depolarization. So our axon is now fully depolarized. Here is a section of the axon showing that it has plus signs on the inside and it is fully depolarized. The membrane voltage is now plus 20 millivolts. At this point, voltage-gated potassium channels open because they are sensitive to the change in voltage. Once the potassium channels open, remember that there is more potassium on the inside, so potassium rushes out. And when potassium rushes out, it takes positive charges out of the cell and the inside becomes negative again. So we say that the axon is now repolarized. We say repolarized because the voltage is going back to the resting membrane potential. So it returns to minus 70 millivolts. So let's see how that happens. So now let's take a closer look at how the ion distribution and proteins and channels work in the repolarization phase of the action potential. Remember that there is more sodium outside and more potassium inside. We're dealing with two different channels here. The sodium channels, which are the voltage-gated sodium channels, close, and the voltage-gated potassium channels open because they respond to the change in voltage. At 0 millivolts, voltage-gated potassium channels start opening, and by plus 20 millivolts, they are fully open, and potassium rushes out of the cell, taking positive charges out of the cell. This causes the voltage to go down. This is the falling phase, or the repolarization phase of the action potential, and the voltage goes back to minus 70 millivolts, or the resting membrane potential.